Hello, in this video we will be looking at relative maxima and minima. Specifically, we're interested in using the first derivative to do a first derivative test. So we have spent a lot of time in this course talking about how to find derivatives. Now we start getting into applications of using derivatives. And the first big idea that we want to highlight is that if you have a first derivative in your hands, it will tell you if a function is increasing or decreasing. Remember that your first derivative is just a rate of change of a function. So if your rate of change, your first derivative, if the rate of change is positive, then a positive rate of change would just correspond to an increasing function. Positive rate of change, your function is increasing. If, though, your rate of change is a negative number, then your function would be decreasing. And the only other thing that could happen is maybe your rate of change was 0, and we've already talked about that a little bit. That would mean that you would have a horizontal tangent line. So with this information, we will be able to analyze functions and determine if they have minimum values or maximum values. And let's talk about how we would use that information. Now, if you're given a graph, you can pretty easily determine where your relative minimum and maximums are. So on this first graph, we have a relative maximum on the left at that peak, and when we get down to this little valley down here, we see we have a relative minimum. On the second graph, there would be a relative maximum on the left and a relative minimum on the right. This question may seem fairly straightforward if you're looking at a graph, but it's a little bit complicated if you only have a function and you don't even know what the graph looks like. So we begin by examining graphs to decide what patterns are going on here. Once we notice the patterns from the graphs, then we will be able to apply this in an analytical sense. Okay, so looking at that first graph, as we move from left to right, the function is increasing, and then we hit the maximum value, and then it decreases. And if you think about what a maximum is, that should seem very natural to you. The only way to get a maximum would be to increase your function to a specific point, the maximum, and then it would have to decrease afterwards. So I'm going to go ahead and write those words down. We increase, and then afterwards we decrease. When you examine what happened around a minimum, the function was decreasing up until you hit the minimum, and then afterwards the function was increasing, and that has to happen anytime we have a minimum. So if you decrease followed by an increase, then that by the nature of being at the bottom, if you decrease followed by an increase, that means you had a relative minimum at the point that you were looking at. Okay, so let's fill in some words down here. For a relative minimum, the first derivative would change from, it would change from negative to positive. If you haven't associated this idea of a negative first derivative with the idea of decreasing, we need to do that like right away. That's what we highlighted up here. So a decreasing function, let me actually put a little bit more information here. F is decreasing. I know that's not spelled right. So if f is decreasing, what that means about its derivative is that f prime has to be negative. It would have to be less than 0. I'm just going to write the word negative. So when your function's decreasing, your first derivative is negative. When your function is increasing, your first derivative is positive. Okay, so we changed from negative to positive. The first derivative changed from negative to positive, and that's what told us we had a minimum. In a very similar manner, if your function increases followed by a decrease, That's how we get maximums. So your first derivative would have to change from positive to negative. The next thing we would want to consider is when could this happen? And what we're going to call it is anytime the first derivative changes from a negative to a positive, or if it changes from a positive to a negative, we're going to call these critical values. In fact, a critical value gets defined a little bit more broadly even than that. A critical value is going to be any place where your first derivative is either 0 or undefined. All right, so here is the definition. A critical value is going to be a value of x where the first derivative is equal to 0 or is undefined. So just a little bit about terminology. A critical value is going to be an x value, like 2, but these always result in critical points of the function, and a critical point is an actual point on the original function. So if your x value was 2, then it has to be x comma y, so something like 2 comma 7. Okay, so based on this definition, what we can say about critical values are places where a relative minimum or maximum might occur. It's not going to actually guarantee that we have minimums or maximums, but what it does guarantee is the only places where your derivative could change from positive to negative or from negative to positive would have to be at critical values. So a place where you got to 0 or a place where the function just became undefined. Now, if this is your first time seeing this, then you might wonder, like, why doesn't this guarantee that we have a critical, sorry, why doesn't a critical value guarantee that we have a relative minimum or maximum? A good counterexample of why that wouldn't be the case would just be the graph y is equal to x cubed. So the y equals x cubed graph looks like this. And what happens is it's a function that increases the entire time. It increases, it slows down, but then it picks back up and it starts increasing more rapidly. Now right here at 0, you actually have a horizontal tangent line. So let me put that information in. Right here, what we have is we have that y prime is equal to 0. So horizontal tangent line, it's a critical value, but we would definitely not call this a minimum or a maximum because the function increased followed by an increase. So when this happens, if your first derivative is 0, but it doesn't change signs as it passes by the critical point, then so it doesn't go from negative to positive or positive to negative, we're just going to call this a horizontal point of inflection. Now, in future sections, we will talk a lot more about what a point of inflection actually is, but for now, it's just like what we are calling this type of behavior. Okay, so let's look at our first example. Hopefully that idea, the basic idea, should be pretty intuitive. In order to have a, I'll even write it down to recap. In order to have a maximum, the function would have to increase followed by a decrease. And in order to have a minimum, the function would have to decrease followed by an increase. And that's the big idea from these notes. Now, on a graph, it looked kind of silly to talk about it that way because it looks obvious to you that you have maximums and minimums. But in this example, you have a function. And if you don't know what the graph of this function looks like, there's no good way for you to just determine, well, there's no visual way for you to determine what, like where the minimums and maximums occur. So what we're going to do is we're going to do something called a first derivative test. This is probably worth like bolding, writing down. The first derivative test is like the name of the thing that we are doing. We are going to use the first derivative to classify all of our relative extrema. Also, if you haven't seen this word before, what is an extrema? An extrema is just a generic word for a minimum or a maximum, but it's nice because a instructor, whoever, can ask about an extrema, and this is a generic word that means you have to think about both minimums and maximums. So it doesn't lead you to think only about one or the other. Okay, so what would the process be? How would we analyze a function then to determine if we have relative extrema or not? What we do is we start by finding the first derivative. After you have found the first derivative, you're going to find critical values. You're going to set it equal to 0, figure out any x value where that is possible. And in some situations, you might see that there are certain x values where your function is undefined, and then those would be critical values as well. Once you find all of your critical values, then we go ahead and find the critical points. Finding those points are fairly easy, because once you have an x value, all you have to do to get the y value, of course, is you plug it into your function. Once you have critical points, these are the candidates. These are maybe relative minimums, they might be relative maximums, but we don't know at this point. So at that point, we go back to the first derivative, and we're going to make what's called a sign chart, where we really kind of dive into, is this function increasing, is this function decreasing, and then based on the behavior of increasing, decreasing, or decreasing, increasing, we will be able to classify things as maximums or minimums. And then if we want, we can, at the end, with all of the information that we have, we'll be able to sketch a graph of the function. All right, let's give ourselves a little bit more room for the example at hand. We have a function, f of x, and we want to compute all of these things. Let's begin by computing the critical values. So I do recommend that as you're showing your work on something like this, that you take a little bit of time to label what you are doing, because there's going to be a lot of work on this page, and just for whoever comes by and looks at your paper next, whether it's your instructor or whether it's yourself when you're reviewing your notes, if you leave little notes about, hey, right here I'm computing critical values, it just goes a long way to allowing your work to be readable. So f prime is going to be equal to, let's see, this would be 4x cubed plus 24x squared. So that is your first derivative. And then you have to recall, what do you know about a critical value? A critical value would be any time your first derivative is equal to 0 or undefined. Now in this case, this function is not going to be undefined anywhere. So we just have to worry about, like, how could it possibly be equal to 0? Okay, so let's do that. 0 is equal to 4x cubed plus 24x squared. We now have the task of solving this. So depending on the example that you were looking at, the algebra of solving this might be a little bit more involved or a little bit less involved. Right now, it's pretty simple. We just pull out a common factor, and that's all we're going to have to do. But there may be further examples in the future where quadratic formulas are necessary, or maybe other factoring techniques. So here, you pull out a common factor of 4x squared. This leaves you with x plus 6. And then we get to decide what does that mean x would be equal to. So x would have to be equal to -6 or 0. We get -6 from this factor, we get 0 from this factor. So we have completed finding all of the critical values. Next thing we would want to do, let me check that off, is we would want to find critical points. So let's go ahead and do this right underneath. Critical points. Again, critical points are just points on a function. They're points whose x values are those critical values. So -6 needs to be an x value, and 0 needs to be an x value. When you're trying to find the y value, remember you're not plugging it into the derivative function, because this is the rate of change of your function. The y value of the function is the y value on that original function. So let me go ahead and write that down. We are plugging in f of -6. I'll go ahead and do that in a calculator, and I get -420. So -420. To get the y value for 0, this one you can do in your head fairly easily. You should just get 12 as the y value for 0. So we now have our critical points. I'm going to pause and just think about what we have done before we go on to the next part. Critical values, these are locations where the function might have minimums or maximums. So the critical points, these are like, this is maybe a minimum or a maximum point on the function. This is maybe a minimum or a maximum point on the function. You might look at the y value and say, hey, negative 420 looks like a minimum, positive 12 looks like a maximum, but you cannot just look at these y values to determine if your critical points are minimums or maximums. It does not work. Sometimes you might get lucky and it works, but there are many cases where it just does not work. So what do we have to do instead? How do we classify these critical points as either minimums or maximums, or maybe they're just points, horizontal points of inflection? What we have to do is we have to make a sign chart. So let me go over here and say I'm going to make a sign chart. Now, a sign chart is just a number line where on the number line, the only numbers you need to record are the numbers of interest, those critical points. We absolutely have to label this sign chart. This is going to be a sign chart of your first derivative, so I'm going to call it a sign chart of f prime. The reason this label is super important is because in future sections, we will examine the second derivative as well, and you might make a sign chart of a second derivative. So if you can imagine what it looks like to have a ton of work across the piece of paper, and if you have just random sign charts that aren't labeled, it's really hard to tell what's going on for yourself and then for whoever's looking at your paper after you. Okay, so we've labeled this. We're going to be thinking about the first derivative. What we are trying to capture in the sign chart is my first derivative positive or negative? Because remember, if we have a negative followed by a positive, you're looking at a minimum. If you have a positive followed by a negative, then you're looking at a maximum. So where is my first derivative positive? Where is it negative in these three areas? How do we determine that? Well, the way we determine it is you have to test values. So I'm going to make a little table here. Let's come up with some test values, and then I'll list what f prime of x is equal to. Okay, the first value I want to pick is just any value to the left of negative 6. You might think about negative 7, negative 8, negative 9, but really anything to the left of negative 6 would work. So you could pick negative 100 as a value. But I think negative 7 is a pretty natural number to pick. What do we do with this test value? We want to know what the first derivative is doing at that value. So we know it's not going to be 0 because the only two times we ever got 0 were those two critical values. So we take negative 7 and we just put it into the first derivative function. You can either plug it into the very first recording of our first derivative, or you can plug it into this factored form. If you're doing it in your head, sometimes plugging it into the factored form is easier, but if you have access to a calculator, they'll both be pretty quick. Okay, let's put negative 7 into this first derivative and see what we get. All right, I get negative 196 when I plug it in. The number itself is not important, but the sign on the number is extremely important. It was a negative number, so that means my first derivative was negative to the left of negative 6. Next, we're going to go look at the second interval in our sign chart. I need to pick a test value in between negative 6 and 0. Let's go ahead and pick, I don't know, negative 2. Any number that's easy to plug in is going to be fine. When you plug negative 2 into this function, we should get 64. And we don't really care that the number was 64. It could have been 65, 66, whatever. But we notice it's a positive number. And because it's a positive number, we record that information in our sign chart. Next, we go test a value to the right of 0. 1 is a pretty natural number to want to pick, but you could pick anything. You could pick 100 as your test value. If we plug 1 into this function, this one I'll do in my head, 4 plus 24 is going to be 28. And again, we don't care that the number was 28. It could have been 280. We care if it's positive or negative, and we notice, hey, that was a positive number. If you want, just put a little plus sign in front of it. That's the point. Okay, so the only reason we made these test values at all was so that we could fill in these plus signs and minus signs on the sign chart. Once you have that, we can now use this information to answer all of the rest of the questions that are being posed up there. Let me go ahead and box. I won't box it in yet. Let's find intervals where the function increases or decreases. So let's start with, I don't know, decreasing. Sorry, this should be an English sentence. So let me say f decreases over. You look at your sign chart. Where was your first derivative negative? Because a negative first derivative corresponds with a decreasing function. And you see it happens anywhere to the left of -6. So I want to write interval notation that says anything left of -6. And if you recall from an algebra class, interval notation keeps track of two numbers. It's the leftmost x value and the rightmost x value. So there is no leftmost x value. We're going to say it's negative infinity. The rightmost x value was -6. So negative infinity up to -6. That is the interval. Then we want to talk about where f increases. Now, it might be tempting to say one thing that's not entirely simplified based on how my sign chart looks. So where is my function increasing? I have a positive first derivative in between -6 and 0. I have a positive first derivative to the right of 0. So the first time you ever do this, if you were with me in class, I made this mistake as well. The first time you ever do this, you might say, well, that first interval is -6 to 0, and the second interval is 0 to infinity, so wouldn't this be where the function is increasing? These are the intervals where your first derivative is positive, but because they butt up next to each other, it would make sense just to say that f increases the entire way. It doesn't really make sense to say it stopped increasing at a point. The idea of a function being increasing, it never relies on a point, it always relies on an interval. So the TLDR is if the two numbers match, we're just going to mash this into one interval. So this will be -6 to infinity. My function increases that entire time. And that kind of makes sense when you think about, okay, we had an increasing function that paused for one instant and then it increased. But if you only pause for like an instant, really you were increasing the entire way. Okay, so we have answered the question. We found intervals where the function increases and decreases. So let me go ahead and block that out. Now that we know that, let's use that information to classify all of our relative extrema. When we classify relative extrema, what that means is take your critical points, and now that you know where the function decreases and increases, you can tell me, are these points minimums? Are they maximums? Are they neither? Okay, so let's examine the first point first. So at -6, the function decreased, then increased. If you like, it's fine if you want to even just draw like a little sketch of the function. You decreased, then you increased. Okay, if your function is decreasing and then increasing, what type of behavior is that? Is that a minimum or a maximum? And clearly, if you do the sketch, hopefully it becomes very clear, you're looking at a minimum value. Okay, so let's write a sentence that says that. F, my original function, has a relative minimum at the critical point that we were looking at. Next, let's look at 0. What happens at 0? Well, the function increases and then increases. So this, by definition, is is what we called a horizontal point of inflection. A horizontal point of inflection is any place where you have your first derivative equals 0, so you have a horizontal tangent line, but it doesn't change signs around that, so it was increasing, increasing, or technically it could have been decreasing, decreasing, but as long as these two are the same, then what we are looking at is a horizontal point of inflection. So let's go ahead and write that down. F has a horizontal point of inflection at 0, 12. What about maximums? We haven't said anything about them. If there are no more critical points, then there are no maximums on this function. So let's write a sentence that says f has no relative maximums. Okay, we have classified our relative extrema. We have determined if the function has horizontal points of inflection. So we have answered every question that was posed to us. The last thing I want to do is I want to sketch a graph of this function. So f is equal to x to the 4, 8x cubed plus 12. F equals x to the 4 plus 8x cubed plus 12. What would a graph of this function look like? Well, what we actually know a lot of information. We have 2 points that the function goes through, so let's label those. If my x value is 0, my y value is 12. We have a point right here. And if my x value is -6, my y value is -420. So we have a point right here. Furthermore, let me scroll up so we can see the sign chart just a little bit. That should be good enough. What we know is the function is going to decrease. What we know is the function is going to decrease all the way up until -6, then it's going to increase up till 0, and then it will increase again beyond that. So in terms of the graph, I'm going to decrease all the way up until I hit the point that I listed, then I will increase up to this point. At the point, I need a horizontal tangent line, and then I'm going to increase beyond that. So let's go ahead and sketch that. I'm actually going to draw in a little horizontal tangent line just to emphasize that, like, the reason that these are critical points is because the first derivative equals 0, which means we have horizontal tangent lines. So the graph decreased all the way up until our first point when the x value was -6, and then we had a horizontal tangent line, and it increased up until this point. And here, we need a horizontal tangent line, so the graph has to flatten out momentarily, but then it's going to increase beyond that. So it continues on in that manner. Now, it's kind of remarkable how accurate this graph is, given like how hard it would have been to have graphed that just by hand. Certainly we could add more detail to the graph if you plug in like the x value of like -1, -2, -3, +1, +2. But even though we would have more detail, we wouldn't have any more interesting details. All of the interesting information is captured in this brief sketch that we've done. Okay, so now that we have one example under our belt, let's go to another one. Hopefully this one we can do a little bit faster. Okay, we have a function, and we want to find critical values, critical points, intervals where we're increasing, decreasing. We're going to classify relative extrema. We are going to look for horizontal points of inflection. All right, from the beginning, what do? We know that we want to find critical values. This happens anytime your first derivative equals 0, so we have to find the first derivative up here. 3 times 1/3 would just be 1. We reduce the size of the exponent by 1. Then we find the derivative of x squared should just be 2x. The derivative of 3x would be 3. So if that's our first derivative, it would need to be equal to 0. We're looking at this like that looks factorable to me. So we get x minus 3, x minus 1. That doesn't sound right. How about x plus 1? There we go. That's equal to 0. So x would have to be equal to 3 or -1. These are the critical values of the function. All right, the very next thing we do is we go look for critical points. What are critical points? Critical points are the points that have x values that are critical values. So once we've done this, we now need to put 3 into the original function. I'm going to pause the video and put it in my calculator. All right, we see that our critical points have these y values. The one that was a decimal, I just converted it to be a mixed number so that we can find it on a graph easily. I don't like seeing mixed numbers, like just as an idea. I would prefer to write this as 13/3, but on a graph, certainly you'll be able to find that a little bit better. We have found our critical points. Next, we need intervals where the function increases, decreases. That means we need a sign chart. And we're going to make a sign chart of your first derivative. So the only values that we record are the critical values. Make sure that your critical values are in order like they would be on a number line, otherwise like things get really crazy. So -1 is to the left of 3, which is a little bit to the right. All right, once we have that, we need to test values and plug them into f prime. All right, I'm going to test -2, I'm going to test 0, I'm going to test 4. Let's plug them into this function over here and see what we get. Once we see the values of our first derivative function, we can fill in the sign chart. The sign chart should be positive, negative, positive, meaning that the graph increased, decreased, increased. Okay, so let's write that down. Where is my graph increasing? And where is my graph decreasing? Okay, to make it make sense in English, I really need to say f is increasing, f is decreasing on these intervals. Okay, so f is increasing from -infinity up to -1, and then from 3 to infinity. F is decreasing from -1 to 3. In this case, we're going to have 2 separate intervals, and we keep them separate because the numbers are not butting up next to each other. So it's just 2 very different intervals where the function increases, and then the place in between, the function is decreasing. This information, yes, it answers this question, but what it's really useful for, and the lines that I drew on the sign chart, what they're really useful for is helping us to identify the points that we are looking at. Is this point 3, -7 a minimum, a maximum, or a horizontal point of inflection? Well, let's look at 3. You decreased and then increased, so decreasing, increasing looks like a minimum to me. So f has a minimum at 3, -7. Let's look at -1. At -1, the function increased, decreased. That looks like a maximum value. So then we'll say f has a maximum at -1, 4 1/3. I'm trying to go fast, and I'm regretting it because I didn't write the word relative in here. You could talk about absolute minimums and maximums, which are very different than relative minimums and maximums. So the thing that we are classifying are relative extrema, so we really do need to call them a relative minimum, a relative maximum. Okay, that takes care of all of my critical points. That means we have no horizontal points of inflection. I think a pretty standard abbreviation for horizontal point of inflection would be this. No HPI. All right, we have classified our relative extrema. We've thought about horizontal points of inflection. So we are pretty much done. Let's go ahead and just draw a quick sketch of the function over here. There'll be homework questions where you have to identify what the graph looks like. You are always going to start by listing, like graphing, sorry, the points that are listed over here as critical points. So I need to plot the point 3 and then -7. Okay, I'm not actually going to keep track of the scale. So 3, -7 is down here, and then -1, and then 4, the third, It's up here. So the sign chart tells me I increased up until -1, then I decreased up until 3, and then I increased beyond that. So I'm going to increase up until I hit the point at -1, then I'll decrease to -7, and then I will increase after that. So this is what the graph should look like. If you like, you can just kind of sketch in like, hey, these were horizontal tangent lines because our first derivative was equal to 0. Okay, the last thing that we would like to do in these notes is we would like to try to think about the graph of a derivative function, and then using that, answer the same types of questions we have been asking before. So if you have never looked at a derivative graph before, your intuition may still need to be developed. You might not immediately just be able to answer these questions. But once you get comfortable with what information is being presented in the graph, then yeah, it's going to be pretty straightforward to answer the questions. All right, so first of all, we want to find critical values of f. All right, so critical values of f. Okay, what we have to keep in mind is that your critical values happen when your first derivative is equal to 0. Well, the graph that I'm looking at is a graph of the first derivative. Now, they told me what it was, so I could literally set it equal to 0 and solve it and come up with my answer that way. But if you don't want to do that, you have the graph, where is it 0? I know the axis is a little bit hard to read. Let me darken this in a bit. Okay, so where is the graph equal to 0? Where is its y value 0? It happens right here, and it happens right here. Let me just make a little note of that. These two places are y value is 0. So, where are my critical values? Those happen at x equals -5 and at 2. Now, you could actually take the derivative and set it equal to 0, and you'll find that those are your answers. But if you're given a graph already, you can just read that information off of the graph. Okay, we have answered the first question. We found the critical values. Where is the function increasing or decreasing? Okay, so for that, we previously came up with a sign chart, and I'm going to do that again. We have our critical values at -5 and at 2. Now, if you wanted, you could start plugging test values into the first derivative function. We could plug -6 into this and see if it's positive or negative, but that information is recorded on the graph. If you go to -6 and you plug it in, what would the y value be? I know it doesn't actually show you the exact number, but when you plug it in, would you have a positive y value or would you have a negative y value? And clearly the graph is going up to the left, so you'd have a positive y value. So what that tells us is that our first derivative would be positive over here. Okay, so over here, this is a positive. Similarly, any value to the right of 2 would be positive. Where do we have negative values on our first derivative? Well, we have negative values anytime the y value is negative, so that's down here. Let's go ahead and record that. This is a negative y value. So your first derivative is negative. I haven't labeled my sign chart yet, so let me label this. Okay, what this means is it means the original function would have been increasing, decreasing, increasing. That's going to be the shape of the original function. Okay, now that we've written the sign chart, thought about how we could get that information off of the graph, let's actually answer what they're asking. Where is the function increasing? Increases of f increases on -infinity up to -5, and then 2 to infinity. F decreases on -5 to 2. All right, let's box some of these answers in. So we found our critical values, we made a sign chart, and we found out where the function was increasing or decreasing. Okay, from that, we should be able to find locations of any relative minimums or maximums. Notice we don't actually have the original function, so we can't say what the maximum value of the function is or the minimum value of the function is, but we can say where it happens because that's just the x value. Okay, so locations of extrema f has a relative minimum at x equals something, f has a relative maximum at x equals something. How do we know if it's a relative minimum or a maximum? Well, let's examine -5, because that was one of our critical values. The function increased, decreased. If you increase, decrease, you are looking at a maximum. Okay, notice I'm not looking at this graph right here. Like it's hard to make my brain look at this and think about a maximum. It's very easy to make my brain look at this and think about a maximum. Okay, technically we had positive first derivative followed by a negative first derivative. That means the function has a maximum, but it's much easier to have a sign chart and say increase, decrease. Hey, that looks to me like a maximum. Okay, so maximum was at -5. Then we think about where would it have a minimum. Well, a minimum happens if you decrease then increase, so that happens at x is equal to 2. Again, it's a little bit difficult to look at this this graph and decide like, yeah, that looks like a minimum to me because I had a negative first derivative followed by a positive first derivative. Definitely, it was worth your time to have made that sign chart. Okay, we have found minimums, we have found maximums. There are no other critical values, so since we've classified them all already, there are not going to be any horizontal points of inflection. Let's sketch a possible graph for the function. All right, so we don't have any like actual points to go through. All we have are x values. So at -5 and at 2, we have these. And so we just need to draw a generic graph that increases up until some point when the x value is -5, then it has to decrease, then it has to increase. I believe in the homework they want you to go through the origin. So if I did this, I'm just going to like put some random point up here, some random point down here. I'm going to increase, then I'll decrease, then I'll increase. Something like that. But yeah, that's just a potential sketch of what it would look like. I know it looks a little bit shaky, but I apologize for that. That does finish these notes, so hopefully that's helpful as you guys are looking at the homework and trying to get these ideas mastered.